In the last video, we talked about electron affinity. We defined it as the energy change when an electron is added to a gaseous atom. And we said, generally speaking, electrons are attracted to areas with a highly exothermic first electron affinity, or highly exothermic electron affinity generally. That level of attraction, that attractiveness between the electrons and the areas of highly exothermic electron affinity, one way of quantifying that attraction is what we call electronegativity. And that's what we're going to focus on in this video. So let's get started. Our formal objectives are the following. We'd like to be able to define the term electronegativity and really understand this definition. Secondly, we'd like to be able to identify and explain the trends in electronegativity, or EN, down a group and across a period. And finally, we should be able to distinguish between EN and EA, or electron affinity. We begin with this first one about defining and understanding the definition of electronegativity. Here's the definition of electronegativity. It's the relative tendency of an atom to attract a shared, or you can call it a bonded pair, a shared pair of electrons towards itself. Tendency of an atom to attract a shared pair of electrons towards itself. But what does that mean? To understand what it means, we need to understand these two statements here. Electron sharing gives rise to covalent bonding. Electron sharing equals covalent bonding. And the goal of bonding is to attain a noble configuration. Goal of bonding equals noble configuration. Let's see if we can understand these statements. You're familiar with this picture by now. We have the first 20 elements and their electronic configurations in the simplified form. And we recall that many of these configurations are relatively unstable, relative at least, to the noble gases. The noble gases are the stable guys, and that's why they tend not to interact with the others. And because these guys are relatively unstable, they tend to play a kind of game of electrons where they're trying to lose, gain, or share electrons in order to attain a noble gas configuration. Notice what I said, lose, gain, or share electrons. What we're going to focus on here is the sharing of electrons. Losing and gaining we'll talk about in another video. So let's see what fluorine could do to attain that noble gas configuration. Fluorine isn't happy at the moment. It only has 7 electrons in its outer shell. It might just find another fluorine. Fluorines tend to hang out in the same places, right? If you have one fluorine atom, you probably have another fluorine atom close by. So they can just do that. They get together, and now fluorine has what? A full outer shell of 8 electrons, just like neon there. And this fluorine also has a full outer shell of 8 electrons, like neon there. Or at least they can pretend that they both have that full shell. So they both get to be kings, you can think. Okay, so back to our statements. The goal of electron sharing, or electron sharing, gives rise to what? To covalent bonding. What is a covalent bond? A covalent bond is the mutual attraction now that these two atoms have to the shared pair of electrons. So they're stuck together by virtue of being attracted to the same pair of electrons. And the goal of bonding, as you can see, is to attain a noble configuration. So they both have that noble configuration now, that neon-like configuration. Let's take another example. Here we have phosphorus, and here we have hydrogen. So phosphorus is in group 15, which means it has, what, 5 outer shell electrons. And the hydrogens are in group 1. So they do that. They get together, and now phosphorus has an outer shell that looks like the outer shell of argon with 8 electrons, even though the colors are off. But electrons don't have colors. So the full shell there of what? Of 8 electrons. And hydrogen looks like helium as well. So again, they're all happy. Okay. Now we have that again, our statement, the goal of electron sharing is covalent bonding. Sorry, no. Covalent bonding gives rise to electron sharing gives rise to covalent bonding. I think I'm tired this morning. So now we have here 3 covalent bonds. And the goal of these bonds is to attain a noble gas configuration, as you can see. So now we understand these two statements, I hope. Let's look at the last example now, and we'll finally arrive at our definition of electronegativity. We take fluorine and we take hydrogen. So what can fluorine and hydrogen do? they can get together, of course, and form a covalent bond. So we're going to demonstrate that. Before we do that, let's change the color of hydrogen's outer electron to make this illustration slightly simpler. And remember that although we've been drawing these electrons as static things, the electrons are actually moving around the atoms. They're not actually moving in these finely defined orbits as we have here. They're moving in orbitals. Hopefully you remember what that is. But we simplify it here as to say that they're moving in these round orbits. Okay? And now we can have the situation like we had before, where these two guys come together and form that covalent bond, sharing those electrons. So they're both kings now. They both look like a respective noble gas. So fluorine looks like neon, hydrogen looks in some sense like helium. But we can think of the sharing as follows. Some of the time, the electron density is sort of hanging mostly around fluorine. So it's as though those two electrons are not really being shared. They basically belong entirely to fluorine. And if you look at hydrogen here, you can see hydrogen is basically bare of electrons, apart from at this small edge. So most of hydrogen here is completely electron free. Just have that positive charge over there. So most of the time, or some of the time, you can see fluorine gets to be king. And some other times, though, you can also think hydrogen gets to be king. So hydrogen now is taking the full electron density of those two electrons and is letting those move around its own atom, right? And so at this point, if we have only one proton here and two electrons, you can see you would have a kind of net negative charge there. But it turns out that most of the time, this is the situation. So most of the electron density is clustered around fluorine, and hydrogen barely gets any electron density. Okay? So I write that experimentally, it is observed that overall electron density is higher around fluorine. Why is this? Due to the greater nuclear charge. Fluorine has 9 protons in its nucleus. Hydrogen has only 1. So fluorine has a greater tendency or ability to pull the electrons towards itself. Okay? So fluorine is more attractive to the shared electrons. Because of this fact, then, fluorine ends up with a partial negative charge. Why is it not a full negative charge? Because it hasn't completely ripped off that electron. If it completely took the electron and formed a fluorine anion like that, then it would be a full negative charge. But it hasn't. It's still sort of sharing it, even though it's an unequal sharing. And hydrogen has a partial positive charge for the same reason. So over here is partially positive because it's relatively starved of electron density. So the proton has most of the power on this end of that molecule. Okay? And we can indicate the direction of polarity with this kind of symbol. So over here we have negative, and over here we have positive. Now, how do we get the term electronegativity? In the following way. Sorry, I've written on top of my text, but it says here, fluorine is partially negative because of the higher electron density around it. Right? Fluorine is negative with electrons. Fluorine is electron negative. Fluorine is electronegative. This is the thought process I imagine the person went through when they came up with this term, but I'm not sure. So now we see our definition. Electronegativity is the relative tendency of an atom to attract a shared or bonded pair of electrons towards itself. The relative tendency of an atom to attract a shared pair of electrons towards itself. So now, who would you expect has a higher electronegativity between fluorine and hydrogen? Of course, it's fluorine, right? This is the Pauling scale of electronegativity. There are a bunch of other scales, but we focus on the Pauling scale for pretty much all lower level chemistry. So fluorine has a 4.0 electronegativity according to the Pauling scale, and hydrogen has a 2.2. Some important facts about electronegativity. Firstly, although this is an extension, so you won't be asked about this, the EN values are calibrated against hydrogen usually. Why? Because it forms covalent bonds with many different compounds. So you bond hydrogen to some other atom, say fluorine, and you experimentally measure how much electron density, or how much is the electron density skewed away from hydrogen. If it's strongly skewed, then you give that new element a fairly high electronegativity. If it's not too skewed, then you give it a fairly low electronegativity. So we could take hydrogen, and instead of bonding it to fluorine, we bond it to, say, oxygen. There you would need 2 hydrogens. And we can measure basically who is pulling those electrons more. So generally we measure it relative to hydrogen, which seems a bit confusing, because then why did they give hydrogen this kind of arbitrary number of 2.2? Well, you need to go read about it. It's not as simple as I make it seem. Okay, now here's another important fact. Most noble gases do not have electronegativity values. You can think why? Well, because they don't form any bonds. So helium and neon, it's really hard to get them to form any bonds, and so you can never measure how much they pull a shared pair of electrons if they never actually get into sharing a pair of electrons. And finally, these values are unitless, as you can see here. We just have 2.2 and 4.0, and there's no unit like we had before with kilojoules per mole and all of that stuff. Why is there no unit? Well, imagine if you said, I don't know, Bob is twice as tall as Jennifer. What's the unit of your twice there? There's no unit, right? Because it's a relative quantity you're talking about. So because these are relative quantities, then there's no unit. Okay, I think now we can say confidently, well, not too confidently, let's look at some questions first, but we can say semi-confidently that we can define and understand our definition, which is the really important part, of the term electronegativity. Let's look at 2 questions to see if this is the case. Which of the following is the best definition of electronegativity? Pause the video, read through the options, see what you come up with. In 2 seconds, I'll show you a clue, and you can pause the video after the clue again. 1 and a 2 and a clue. Read through that if you like. In 2 seconds, I reveal the answer. 1, 2. Here's our answer. Our answer is C. Okay? So A, the energy required for an atom to gain an electron, we've never talked about anything like that. The attraction between the nucleus of an atom and its inner shell electrons, we haven't talked about anything like that. And this last one is the correct definition of electron affinity, which is not what we're talking about. So C is the answer. The attraction between the nucleus of an atom and a bonding or a shared pair of electrons. Okay, maybe I should have put relative here. Relative. Which of these is not true about electronegativity? Again, pause the video, read through the options, think about it. In 2 seconds, I'll show you a clue. 1 and a 2 and a clue. Again, pause if you need to. In 2 seconds, I reveal the answer. 1, 2, and an answer. So C is not true about electronegativity. Electronegativity is not a property of molecules. Atoms need to get into molecules for you to measure the electronegativity, but it's still a property of atoms. You don't say hydrogen fluoride has an electronegativity of 3 or whatever. You say hydrogen has a certain electronegativity and fluorine has a certain electronegativity. Okay? So it's a property of atoms, that's correct. It is unitless, as we discussed, and this is a correct definition for electronegativity. So that's also correct. Okay, now we get a green light with this one. Let's move to the next one of identifying the trends in EN down a group and across a period. We get back to our picture again, but now I've added at the bottom the electronegativity values for all of the first 20 elements. You can pause and see if you can notice any general trends. The first trend is that there's a general increase across a period until we get to the noble gases, which have no electronegativities. Why is there an increase in electronegativity across a period? Well, the same reason we've given for everything else: atomic radius and nuclear charge. So the atomic radius is decreasing across the period, right? So fluorine there is smaller than lithium, as you can see. Its electron cloud is smaller. And therefore, the shared electrons are closer to the nucleus. So if fluorine is sharing electrons, the electrons would be fairly close to fluorine's nucleus, and so the pull on those electrons is stronger than if lithium were sharing electrons and they're so far from that nucleus. And secondly, the actual nucleus, the charge in the nucleus that's pulling, is larger in fluorine. We have 9 protons in there relative to the 3 protons in lithium. And so the pull is stronger. How about the trend down the group? We can see electronegativity reduces down the group. It decreases down the group. Why does it decrease? Same reasons: atomic radius and nuclear charge. Oh well, nuclear charge doesn't affect it. We'll talk about that. So atomic radius is what? Is increasing down the group. So the shared electrons would be further from the nucleus. So here you would have shared electrons fairly close to that nucleus and therefore highly poled. Here we have them far away from the nucleus and therefore only very lightly poled. Now you might think, well, the nuclear charge is increasing. We go here 1, 3, 11, and 19. So there should be more protons to pull the electrons, but that is canceled out by shielding. So here, even though we have 19 protons, we have 18 electrons in these 3 shells here, and so they're hiding most of that positive charge. So the shared pair of electrons isn't too strongly pulled. Again, these are the same explanations we've given for pretty much every trend we have explained so far. Here's the trend for the full first, I don't know, some number of elements here. And as you can see, it's one of the cleanest trends we've seen. We've looked at these pictures for the other ones, electron affinity and ionization energy, and they weren't this clean. Here it's messed up a little bit by the transition metals, but for the most part it's really quite clean. You can see the increase in electronegativity across the groups, and you can very clearly see as well, across the periods I mean, and you can very clearly see the decrease down the groups. So you can see it here down groups 1 and 12 and 2, and over there you can see it very clearly for groups 17. And then here you can see the missing noble gases. For some noble gases, they've managed to get them to bond with other elements, and therefore they can work out their electronegativity. But for most of them, they have not. So now we have the orange light for identifying and explaining the trends. Let's try some questions. This one asks, which of these arranges the halogens in order of increasing electronegativity? As always, pause the video, think about it. In a few seconds, I'll show you a clue which really contains the answer. Here's our clue. Again, pause if you need to, and then I reveal the answer. 1, 2, and the answer. Answer is D. Okay, so fluorine is the most electronegative than chlorine, then bromine, then iodine. A very clean trend down the group. Now, of course, electronegativity values are in your data booklet, as are many of these. So if they ask you this, and if you've forgotten the trend, you can just go in there and refresh your memory. Here's another one. Which of these correctly explains why electronegativity increases across a period? As always, pause the video, read through the options. In 2 seconds, I show a clue. 1, 2, clue. If you need to, pause. In 2 seconds, I reveal the answer. The answer is B. So the nuclear charge is increasing across a period. So we go here 3, 4, 5. Those are too small for you to see, but generally the number of protons increases and the number of shells stays the same. So the electrons are pulled closer to the nucleus. The others don't make sense, so electron affinity becomes more endothermic. That is a false statement. Nuclear size decreases. This is true. Nuclear size does decrease across a period. And new protons are added. Oh no, this is not true, sorry. So atomic size decreases across a period, but the actual size of the nucleus increases. But most of the space of the atom is the electron cloud, not the nucleus. So the nuclear size decreases is false, okay? Even though new protons are added. So nuclear size increases as new protons are added. And ionization energy decreases, that is also a false statement. Okay, we're done with this one. Let's finally try to understand the difference between En and Ea. Hopefully you kind of already get the difference, but we will look at it with some more detail now. So here are the pictures for Pauling electronegativities and the first electron affinities. Pause the video and see if you can notice any kind of relationship between these two. What we see is that generally highly exothermic electron affinities, like here, around the halogens, for example, which means that there's lots of energy released when an electron falls into the atom. Hopefully you remember what electron affinity is. Those highly exothermic electron affinities are correlated with high electronegativities. How can we think about this? I've given you this analogy before. Let's go over it again. So we had said that you can think of the electrons as balls. If you throw balls onto the surface, this periodic table of first electron affinities here, you should expect that the balls are going to want to go into the deep holes. So the places where there will be a lot of energy release, that is a big fall, therefore a high electron affinity, those are the places that the balls are going to want to go, right? So high electron affinity generally means a sort of energetic valley. We kind of have an energetic valley here. That is, the electrons would go into a fairly low energy state when they fall into those spaces. Okay? And electrons and everything else in nature like in energetic valleys. So if you put a ball on the side of a mountain, it's not going to go up the mountain, it's going to go down into the valley. Because things like to fall down energy gradients. It's just a general law of nature. All right, so generally speaking, the electrons are going to want to go into places where they release lots of energy as they come down. Places where there's a high electron affinity or highly exothermic electron affinity. So generally then electrons behave as if they are attracted to these energetic valleys, and that attraction is the electronegativity. Hopefully that makes sense. Let's now look at this table that compares ionization energy, which we've discussed, electron affinity, which we've also discussed, and electronegativity, which we were just introduced to, in a kind of formal sense. Let's clean out the board and start from scratch. And I will, for the most part, just ignore the ionization energy. Focus on the difference between these two, because that's the most relevant for us at the moment. So here was a picture we had for electron affinity. We said that an electron falls into an atom and releases a certain amount of energy, which we call the EA. And in the process, it creates a negatively charged anion. For the picture for electronegativity, you can see there's no electron transfer. We have here a shared pair of electrons, and we're just trying to indicate which one has a stronger pull on that shared pair of electrons. There's no electron adding or removal. What are the analogies we used? Here, we said an electron is falling into the atom. It's kind of like a spaceship falling back into the gravitational pull of our planet. And in doing that, if you've watched enough space movies, you notice that the things tend to heat up. So that's the energy release here that is equivalent to or analogous to the electron affinity. Here you can think of it as we have two magnets fighting for some metallic object in between, say an earring or something. Okay, and that one with a higher electronegativity has a stronger pull on that object being fought for. In terms of definitions, for this, we've gone over this definition many times. It's the energy change when an electron is added to a gaseous atom or ion, whereas that is the tendency to pull a shared pair of electrons. For EA, we had the first EA, which is the energy to remove, energy change when an electron is added to a neutral gaseous atom. So a neutral gaseous atom, which means we're still adding the first electron. So first EA is energy for the addition of the first electron. The second EA is the second electron, and so on. For these, we don't have first, second, third, right? Because there's no electron addition or removal. The equations here, you remember this equation. Here we start with neutral. We add a negatively charged electron. We end up with an anion. There's no equation. What is the sign? This sign here is usually negative, as you can see here, negative 59.6 kilojoules per mole, because that indicates that energy has left the system. So here energy leaves the system as the electron falls into the atom. So the energy goes out of the system. Kind of like how here the energy is leaving this object here. That sign is positive, but it doesn't really mean anything what the sign is, because it's a unitless quantity, as we said. So they could have well made it a negatively signed thing. So it's meaningless, the sign. The trends are similar. So here we get more exothermic across a period, and also less exothermic down a group. So the overall trend would look something like this. Okay, And there, the overall trend for electronegativity also looks something like that. And here is the stuff for ionization energy if you want to compare them and maybe take notes. So now we've covered 4 different periodic trends. We've looked at the atomic radius. We've looked at the ionization energy. We've looked at the electron affinity. And finally, we just looked at the electronegativity. How can you keep track of all of these trends? What I recommend is that you memorize the phrase, fluorine is small but mighty. And once you know what fluorine is, then you can deduce the overall trend, since fluorine happens to be at the top right. So here we have you can visually see the atomic radii of the first 20 elements, or at least you can see the trends in those. Then here we can see the ionization energies, the electron affinities, and the electronegativities. Let's notice what's going on with fluorine in each case. In this case here for atomic radius, we see fluorine has one of the smallest atomic radii. Well, why? First of all, it's in period 2, so it only has 2 shells. This has 2 shells, 3 shells. Here we would have 4 shells and 5 shells and so on. And so that means the trend must go like this. So it gets smaller as we go up a group, or larger as you go down a group, however you like to say that. And fluorine has a small radius for a group 2 atom. As you can see here, fluorine is relatively small compared to lithium, which means therefore that the trend is decreasing across a group. Across a period, I mean. Why is it decreasing? Well, because fluorine's nuclear charge is increasing. So fluorine is getting stronger at pulling its electrons towards itself. Here we have 3 protons, 4 protons, 5, 6. So here, by the time here we get 9 protons, those 9 protons are pulling very strongly on this electron shell. And so that makes it a small atom relative to these ones, like lithium and beryllium. So if we know those 2 trends there, then we know that the overall trend for atomic radius looks like this. And like that, that makes it easy to answer questions. So fluorine is small, as we can see there. Fluorine is mighty, though, because for the next 3, it is the most, or the highest. It's always the most something. So fluorine is one of the most, in terms of ionization energy. It has one of the highest ionization energies. Why is this? Because of large nuclear charge and a small radius. Ionization energy is how hard is it to pull an electron off of an atom. It's going to be really hard to pull an electron off of fluorine because it's so small, that is, the electrons are really close to its nucleus, so they're going to be held on really tightly. Okay? And it has a large nuclear charge relative to this period. So it has 9 protons holding on to those electrons, and so it's hard to remove. So small radius, large nuclear charge gives it a high ionization energy. Small but mighty. Small but mighty again for electron affinity. So for the same reasons that we described here, if an electron were to fall into fluorine, which is what the electron affinity is, if an electron falls into fluorine, how much energy is it going to release? Lots of energy, because it's falling into a highly charged proton, or it's falling close to a highly charged proton. So it has a large nuclear charge, fluorine, relative to its size. So when an electron falls into that shell there, it will release a lot of energy. And so you can see there then that fluorine has one of the highest, or the most, exothermic electron affinities. So highest in this case doesn't work, because as you can see, we generally start from 0 and then we go to negative for the electron affinities. So it has one of the most exothermic electron affinities for the reasons that I've explained down there. Then for electronegativity, again for the same reason, it's a small atom, but it has a large nuclear charge. That means then that if you had some guy trying to share electrons with fluorine, let's say hydrogen here, that's too big for hydrogen. Anyways, then those electrons are very close to fluorine's highly charged nucleus, and so fluorine is pulling them more strongly, which means fluorine has a high electronegativity. So then this trend, we can see that fluorine is the smallest, but for the others, we can think of fluorine as being the most. So here it has the highest ionization energy, which means the trend must look like that. Here it has the most exothermic electron affinity. Even though it's a negative value, we can still think of this trend as looking like this. Okay? So we can think of that as representing the absolute value. Here as well, it seems to decrease down a group, increase across a period for an overall trend that looks like that. So you can see they all basically look like this, with fluorine being the most or the highest. And that is because fluorine is small, as you see from this trend, and it has a highly charged nucleus for its size. So now I think we understand the difference between En and Ea. Let's try just one question and we'll wrap up. Here's one. Which of the following is an accurate description of highly reactive nonmetals? Pause the video as always. Think about how you would answer this. Read through the options. In 2 seconds, I show you a clue. 1 and a 2 and a clue. In 2 seconds, I reveal the answer. Pause again if you want to process this. Here's our answer. C. So it has a high electronegativity. If it's a highly reactive nonmetal, like fluorine here, fluorine is the most reactive nonmetal. And so as you can see, it has a high electronegativity and a highly exothermic electron affinity. And those are related for reasons we have discussed. The others have to be wrong by virtue of the fact that they say different things from C. So C is the correct answer there. Hopefully you got that right. If you didn't, you need more practice. I'll put some practice on the website. In the meantime, I wish you farewell and good luck. Bye-bye.